Usually, when we sit down to do one of these deep dives, we're looking at a trend, something that's been building for a while, the history of the iPhone or the slow rise of EVs.
Right.
But today feels a little different. We are looking at a single date, February 5th, 2026.
It really does feel like one of those before and after moments, like the day the first web browser launched or the day deep learning first recognized a cat video.
Okay, so set the scene for us. It's February 2026. We've had AI writing code for a few years. I use it, you use it. We have AI that can help debug things. So when Anthropic drops this paper evaluating and mitigating the growing risk of LLM-discovered 0 days, my first reaction was, okay, another model update. Why is this one the inflection point they claim it is?
It's the difference between a tool that helps you write a sentence and a tool that can independently dismantle a novel. I mean, until now, AI has been great at what we call copilot tasks.
Right, you're the captain, it suggests a line of code.
Exactly. But this paper from Nicholas Carlini and his team, it shows something new. They took Claude Opus 4.6, dropped it into a code base, and it didn't just write code, it went hunting.
Hunting for 0 days.
0 days. High-severity vulnerabilities that no human knows about yet. The vendor has had 0 days to fix them because they don't even know they exist.
And these are the crown jewels of cyber warfare.
Absolutely. If you have a 0 day in, say, a major piece of software, you can bypass passwords, you can steal data or crash systems, and there's no defense because there is no patch.
And usually, finding these things is incredibly hard, right? I imagine people in hoodies drinking mate in a dark room for 6 months just to find one bug.
It's incredibly labor-intensive. It requires a deep understanding of memory management, logic, all these obscure protocols. Or, it requires massive server farms running for months and months.
Right.
What Anthropic showed is that an AI running on a pretty standard setup can now do this at scale, finding bugs that have been hiding in plain sight for decades.
That's the part I want to drill into, the how, because we're not just talking about it getting lucky. We're going to walk through 3 specific examples from the paper where the AI actually sought its way through the problem.
Yeah, the reasoning is the key.
But before we get to the cases, how do they even set this up? Do they give the AI a cheat sheet like, hey, look, in line 402, there's a typo?
No, and that's critical. They created a headless environment. Think of it like a virtual machine, a computer inside a computer. They dropped Claude Opus 4.6 in there with totally standard tools. Python, a debugger, a fuzzer, but, and this is the important part, no special harnesses.
Define harness for me.
So in security research, a harness is a piece of code you write specifically to test another piece of code. It's like building a test rig for a car engine to rev it outside the car.
I see.
Usually, humans have to build that rig first. Here, the AI had to look at the raw code, figure out how it worked, build its own test rig, and then attack the software.
So it's like dropping a mechanic into a garage with a random engine block and saying, figure out what this is, get it running, and then tell me how to blow it up.
That's a really good analogy. And to appreciate why this is new, you have to understand what we've been using for the last 20 years. Fuzzing.
I love the term fuzzing. It sounds so harmless.
It's basically brute force chaos. A fuzzer is a program that generates random garbage data, weird numbers, long strings of text, emojis, whatever, and just hurls it at the software millions of times a second.
Just waiting for something to break.
It's the monkeys with typewriters approach. If you throw enough random junk, eventually you might hit a combination that crashes the program. It's effective, but it's dumb. It doesn't understand the code. It doesn't know why it's crashing. It just knows that if it types A 5 million times, the system dies.
So the fuzzer is blindly banging on the door. And Claude?
Claude reads the blueprints. It looks at the code structure. It reads the comments developers left. It looks at the history of the project. It reasons. And that's why it found bugs that fuzzers, which have been running on these open source projects for years, completely missed.
Okay, let's get into the detective work. The first case study is a tool called GhostScript. I feel like I've seen that name when I'm installing stuff on Linux.
You definitely have. GhostScript is everywhere. It's a utility for processing PDFs and PostScript files. If you print something or convert a file, GhostScript is often the engine doing the heavy lifting. It's old, battle-hardened code.
So presumably, people have been trying to break this for a long time.
For decades. And initially, Claude tried the standard stuff. It ran a fuzzer. It looked for obvious typos. It found nothing. The code was solid.
So what changed? How did it find a crack in the armor?
It stopped looking at the code as it exists today, and it went back in time. It pulled the git commit history, the log of every single change developers have ever made.
It read the diary.
It did. And it found a specific change in a file called gstype1.c. A developer had added something called stack bounds checking.
Okay, keep it simple for me. What is stack bounds checking?
Imagine a stack of dinner plates. You can only stack them so high before they wobble and fall over.
Right.
In computer memory, a stack holds temporary data. If you put too much data on it, too many plates, it overflows and corrupts the memory next to it. That's a crash, or worse, a vulnerability. The developer realized this function didn't check the height of the stack, so they added a safety rail. If the stack is full, stop.
Okay, so the developer fixed it. Good job, developer. Why is this a vulnerability?
Because Claude asked a very, very human question. If they made this mistake here, did they make it anywhere else? It's a technique called variant analysis.
Oh, that's clever. It's like if I find a typo in a legal contract, I'm immediately going to scan the rest of the document for the same typo.
That is the exact intuition. So Claude took that logic and scanned the entire rest of the codebase. It found another file, gwpsfx.c, that used the exact same logic but didn't have the fix. The developer had patched one hole but missed the identical hole in the other room.
And the fuzzer wouldn't find that because...
Why?
Because to a fuzzer, that vulnerable code is just deep inside the system. Unless it randomly guesses the perfect sequence of inputs to trigger that specific function with a full stack, it just sails right past it. Claude knew exactly where to look because it understood the intent of the previous fix.
That is genuinely impressive. It used history to predict the present. Okay, let's move to the second one. The surgeon. OpenSC.
OpenSC. Yeah, this is middleware for smart cards. So think identity badges, encryption tokens, high security stuff.
And again, fuzzing failed here.
Completely.
Yeah.
So Claude switched gears. Instead of looking at history, it used a semantic search. It started hunting for risky coding patterns. It looked specifically for a function called strikeCat.
StrikeCat, string concatenation. I do this in Excel all the time.
Yeah.
Cell A1 plus cell B1. Why is that risky? Well, in Excel or Python, the computer manages the memory for you. If you combine two huge words, the computer just makes a bigger bucket to hold them. In the C programming language, you have to build the bucket yourself, manually.
I see where this is going.
StrikeCat is notorious because it doesn't check if the bucket is big enough. It just pours. If you have a pint glass, the buffer, and you pour a gallon of water, the data into it using StrikeCat, the water spills all over the table. In a computer, that spill overwrites other code, which hackers can use to take control.
So Claude is just scanning for anyone using this dangerous pouring technique.
It found a spot where the code took a file name, added a slash, and then added another path. It was pouring into a buffer of 496 bytes.
That seems like a decent amount of space for a file name.
It is, and that's why humans missed it. Under normal circumstances, you'd rarely, if ever, hit that limit. But Claude looked at it and reasoned, I don't care if it's rare. If I can create a file name that is 4,100 bytes long, StrikeCat will let me do it, and it will crash the system.
But hold on. If StrikeCat is so famously bad-like, coding 101 don't use this, why didn't the regular tools catch it?
This is the classic needle in the haystack problem. To actually reach that line of code, the program had to be in a very specific state. You needed a specific type of smart card context initialized in a certain way. A fuzzer trying random inputs would statistically almost never stumble into that specific state.
So the fuzzer is stuck in the lobby, and the bug is in the penthouse bathroom.
And the fuzzer doesn't know how to use the elevator. Claude, however, read the code, saw the StrikeCat in the penthouse, and then worked backward to figure out how to call the elevator to get there. It constructed a targeted attack to trigger that specific line.
Okay, so we have the detective reading history, the surgeon finding bad habits. Now we have the third one, which you call the logician. This is the GIF library, CGIF.
This one, to me, is the one that really stood out to the researchers at Anthropic, because this wasn't about a typo, and it wasn't about a bad function like StrikeCat. This was a pure logic error in a complex algorithm.
This involves LZW compression, right? Which is how GIFs shrink files.
Correct. Now, we need to get a little technical here, but stay with me. The fundamental rule of compression is input comes in, compressed output comes out, and the output should be smaller than the input.
That's the definition of compression. If it gets bigger, you're doing it wrong.
Usually, yes. The programmers of this library assumed that output size would always be less than or equal to input size, so they allocated memory for the output based on that assumption.
I feel a but coming.
But Claude realized that assumption is false in one very specific, mathematically weird edge case.
How can a compressed file be bigger than the original?
So think of how LZW works. It builds a dictionary. If it sees blue pixel, blue pixel, blue pixel, it writes blue by 3. That saves space. But that dictionary has a size limit. In this case, 4096 entries. When the dictionary gets full, it has to reset itself to start over.
Okay, so it throws out the shorthand and starts building a new list.
Right. Now, imagine a worst-case scenario. You have an image with just widely random colors, no pattern. So blue, red, green, yellow. You can't compress that. You just have to write blue, red, green, yellow.
So no space saved.
But it gets worse. Every time you write those pixels, you're filling up the dictionary. If you force the dictionary to fill up and reset constantly, you are adding the reset command into the file over and over again, plus the uncompressible data.
So you have the raw data plus all the overhead of the dictionary instructions.
Resulting in an output file that is actually larger than the input.
And because the programmers assumed that was impossible?
The bucket they set aside wasn't big enough? Buffer overflow? Crash.
That is wild. So Claude had to understand the math of the LCW algorithm to realize that this edge case even existed.
It had to simulate the logic of the compression in its own mind. A fuzzer would never, ever find this because generating a file that creates that specific worst-case dictionary cycle is statistically impossible by chance. You have to design the file to fail that way.
Okay, so those are 3 examples. But the paper mentions a much scarier number, 500.
Over 500. Anthropic claims they have validated over 500 high-severity vulnerabilities in open-source software using this method.
Now, I have to play skeptic here.
Right.
We all know LLMs hallucinate. I asked ChatGPT for a bio of a celebrity, and it just invents a spouse.
Right.
Did Claude just make up 500 bugs? Did it send developers on a wild goose chase?
This is a crucial part of the paper. They couldn't just take the model's word for it. They built a validation pipeline. Essentially, they made Claude act as both the researcher and the editor.
How does that work?
So one instance of the model would say, hey, I think there's a bug here. Then a second pass, sometimes a different prompt or model configuration, would critique that finding. It would check, is this actually reachable? Is this just a misunderstanding of the code?
So it's debating itself.
It's self-correction. And then for the ones that pass that filter, they tried to generate a proof of concept, an actual crash. If the model could produce a file that crashed the software, well, there's no hallucination. The crash is real.
That explains the validated part. But why open source? Is this just a charity project?
It's strategic. Open source is the foundation of the internet. It's in your banking app, it's in hospital systems, it's in the power grid. But these projects are often maintained by, 2 guys in Nebraska in their spare time. They don't have a security team.
Good point.
Anthropic focused there because fixing lib whatever makes the whole ecosystem safer.
But here is the dark side, and we have to talk about it. If Claude can find these bugs to fix them, can't a bad actor take Claude, strip off the safety rails, and just say, find me a 0-day in the U.S. banking infrastructure?
This is the dual-use dilemma. The same hammer builds the house or breaks the window. It's the central problem of AI safety.
So what prevents that?
Opus 4.6 introduces a new layer of safety called probes.
That sounds invasive.
It sort of is. Think of it like an fMRI for the AI. They aren't just looking at the AI outputs. They are monitoring the internal neuron activations of the model while it's thinking. They've trained these probes to recognize the brain activity associated with cyber attacks.
So even if I speak in code or try to trick it, the pattern of its thinking gives it away.
That's the theory. If the model starts thinking about how to exploit a buffer overflow in a malicious way, the probe triggers and boom, cuts the connection.
That sounds great for safety, but doesn't that make it hard for the good guys? If I'm a legitimate researcher trying to debug my own code, won't the system slap my hand?
It does. The paper admits this is a major trade-off. It creates friction. Legitimate security research looks a lot like hacking because, technically it is.
Right.
The paper argues that for now, the benefit of fixing 500-plus bugs outweighs the annoyance to researchers, but it's an uncomfortable balance.
And this leads us to the future, the inflection point. Because if this works, if AI can find bugs faster than humans, what happens to the entire industry?
The industry breaks, or rather, our current processes break. We have this standard called the 90-day window. If you find a bug, you tell a company, and you give them 90 days to fix it before you tell the public.
Which seems fair. Give them time to patch.
It was fair when bugs were found by humans, one by one. But imagine if an AI tool releases 1,000 new critical bugs every single day.
The companies would drown. They couldn't possibly keep up.
Exactly. You cannot triage that volume with human teams. The inbox itself becomes a denial of service attack. The paper argues that we are moving to a world where the speed of offense of finding bugs is about to go exponential.
So the defense has to go exponential too.
We have to automate the fix. We need AI that doesn't just say, here's a bug, but here's the bug, here's the patch, I've already tested the patch, and it's ready to deploy.
A world where code heals itself.
We don't really have a choice. I mean, the window where humans can manually review every security update is closing fast. We are entering the era of automated warfare and automated defense.
That is a lot to process. It feels like we're handing over the keys to the castle because the castle's getting too big for us to guard.
I'd argue we're hiring a better guard. But yes, the role of the human is absolutely shifting from doer to overseer.
Well, on that note, next time your computer asks you to restart for an update, don't hit "Remind me tomorrow." There might be a silicon detective that worked very hard to find that bug for you.
Stay curious and please stay patched.
We'll see you in the next Deep Dive.